So in this video, we are going to discuss about the basic concepts of magnification and resolution. So let's look at what is magnifications. So this is a compound microscope, and this is a specimen we are actually looking for. So this is a specimen. So when viewed through the microscope, we will get a larger image. So this is a larger image. This is the size of the specimen with an unaided eye, and this is a specimen through the instrument. So what is magnification? Magnification is the ratio of the retinal image with the instrument. So this is the retinal image with the instrument divided by the size of the retinal image with the unaided eye. So this is the normal and divided by the its largest size. So this is called the magnification. And normally the microscope has two lenses. One is called the ocular lens. So this is the ocular lens or the eyepiece, and the objective lens. So these three are the objective lens. These lenses have the magnifying power, and the magnification of the object can be obtained by multiplying the magnifying power of the ocular and objective lens. So ocular lens and objective lens multiply you will get the magnifications. So for examples, with an ocular lens of 10x magnification and the objective is 40x, the object will be magnified 400 times. So this is the ocular lens which has a power of 10x. The x stands for the actual size of the image. So 10x means it makes the specimen 10 times larger than it. And the objective lens 40x means what? It makes the object 40 times larger. So the whole magnification process is 10x into 40. That means the 400 times. So if the actual size of the object is x, it makes the magnification of 400 times bigger. So this is called magnifications. Now let's move on to the resolving power of the microscope. Here we have three images. This is the first one, is known as unresolved. Here is the second one, just resolved, and this is the fully resolved images. Here there are two images, but you cannot see it as a two images, but it is merged together. You cannot, so this is called unresolved. You cannot see it as a two separate image. So just this is called unresolved. And this is just resolving and not completely separated. Here the two images are completely separated and you can distinguish two images. So this is called a fully resolution. So this power is called resolution. So resolution means the ability to distinguish between two objects is called resolutions. Let's look at the definition. Resolving power refers to the ability of magnifying instrument, here it is microscope or telescope, to separate the details of two closely placed objects. So these are the two closely placed objects and you can see the details here. So another definition is the smallest distance. So these two objects are closely placed, so there are little bit of space is there. So this smallest distance between the two objects which can be identified as a separate image with the aided eye. So this is another way of defining resolving power. The smallest distance between two objects which can be identified as a separate image. A ചെറിയൊരു ഡിഫറൻസ് അവിടെ ഉണ്ട്, ചെറിയൊരു ഡിസ്റ്റൻസ് ഉണ്ട്. ആ ഡിസ്റ്റൻസിലൂടെ ആ മിനിമം ഡിസ്റ്റൻസ് എങ്ങനെ ആ രണ്ട് ഒബ്ജക്റ്റിനെയും വേറെ വേറെ തിരിച്ചറിയാനുള്ള ആ മിനിമം ഡിസ്റ്റൻസ്. So that is called the resolving power. So resolution is the ability of the lens to separate or distinguish between small objects that are close together. Normally the resolution power of the unaided human eye is 100 micrometer. That means if there are two objects, suppose this is a two objects, and is the distance between these two is below 100 micrometer, then you cannot see it as a two images. അപ്പോൾ ഈ രണ്ട് ഇമേജ് ആയിട്ട് കാണണമെങ്കിൽ the minimum distance should be between them is 100 micrometer, below which you cannot see it as a two image. So the resolution power of unaided human eye is 100 micrometer. So these are the different images. This is two images. You cannot see it as two separate images. It's just resolving, and there is a clear separation, and this is completely resolved. So this is, as it goes down, the resolving power decreases. As it goes up, it gets completely resolved. Let's look at the equation for the resolution of microscope. So this is called Abbe equations. So the LM, or a limit of resolutions, or the D, is equal to 0.612 lambda divided by n sin alpha. Here the LM stand for the limit of resolution or the resolving power. Resolving power means what? Ability to distinguish two objects. രണ്ട് ഒബ്ജക്റ്റിന് വേറെ വേറെ കാണാനുള്ള capacity. And this one, that is a 0.61, is a constant. 0.61 is a constant describing the degree to which the point can overlap and still can be recognized as a separate point by an observer. So this. Now the third one is the lambda. Lambda is the wavelength of the light used to illuminate the object. നമ്മൾ മൈക്രോസ്കോപ്പ് ഉപയോഗിക്കുന്ന സമയത്ത് ലൈറ്റ് ഉപയോഗിക്കില്ലേ, ആ ലൈറ്റിൻ്റെ വേവ് ലെങ്ത് ഏത് ടൈപ്പ് വേവ് ലെങ്ത് ആണ് ഉപയോഗിക്കുന്നത്? ലാർജർ വേവ് ലെങ്ത് ഉള്ള ലൈറ്റ് ആണോ ഷോർട്ടർ ആണോ എന്നുള്ളതാണ്. ദിസ് ഈസ് ദ വേവ് ലെങ്ത് ലാംഡ. And third one is the n sin alpha. This one, n sin alpha. So third factor. So this is also known as numerical aperture. NA stands for the numerical aperture. So what is the numerical aperture? Is the ability of the lens to collect the light from the specimen. So this is a objective lens. This is the objective lens. So this lens has the capacity to collect the light from the specimen. So this is a specimen. So this is the light falling on the lens. So this is called the numerical aperture. Simply called the numerical. So the ability of the lens to collect the light from the specimen is called numerical aperture. So the numerical aperture, that ability to collect the light from the specimen depends on two factors. One is called the N. N is the refractive index of the medium. Here in between the objective lens and the specimen, the medium between the specimen and the object, this one is the, here it is refers to as a medium, maybe air or water or oil, something like that. So the numerical aperture depends on the refractive index. Refractive index means what? Is the density of the medium in which the microscope is placed. Sin alpha is a sine of the half angle of light entering the objective lens from the specimen. So this is the specimen here. So this is a specimen. So the light from the condenser passes through the specimen and forms a cone here. This forms a cone. This is the optical axis. This is the optical axis. So it creates an angle here. So this angle is called the angle of aperture. Angle of aperture. So the objective aperture angle, or called the sin alpha. Sin alpha. Density of the air is 1. Water is 1.33. Glycerin is 1.47. and oil is 1.518. There is another oil, Cedar oil. This is 1.66. ഇതിൻ്റെയൊക്കെ refractive indexes different ആണ്. Now the question is, how can we have a better resolution? ഈ ഒരു പാരാമീറ്റേഴ്സ് വെച്ചിട്ട് എങ്ങനെയാണ് ഒരു ബെറ്റർ ആയിട്ടുള്ള റെസൊല്യൂഷൻ കിട്ടുക? For that, the limit of resolutions, or the LM, is inversely proportional to the wavelength of light. അതായത് wavelength കുറയുന്നതനുസരിച്ചിട്ട്, if the wavelength is smaller, that means you get a better resolution. You get a better resolution. So one of the method to have a better resolution is reduce the wavelength of the light. So the highest resolution can be obtained of the light of shortest wavelength, that is 450 to 5 nanometer. That is normally comes the blue end of the visible spectrum. The blue light gives the maximum resolutions. So the first point is better resolution can be obtained by decreasing the wavelength. And the second one is by increasing the n sin alpha, or the numerical aperture. N. Either you can increase the refractive index of the medium, and also you can increase the sin alpha. If you increase the refractive index and the sin alpha, you will get a larger numerical aperture. So if the numerical aperture is larger, that means the greater resolution. Now, in a common microscope, the light that strikes the specimen after passing through the condenser, so there will be a condenser here, the lens, the condenser lens. So the light passing through the condenser and passes through the specimen, which is the specimen here, and it forms, then it goes to the objective lens like this and forms a cone shape. So this is cone shaped, and if the cone has a narrow angle, just like here, and tapers to a point and does not spread too much, ഒരുപാട് spread ചെയ്യില്ലെങ്കിൽ, after leaving the slide, this is a slide, after leaving the slide does not form a separate image and causing low resolution. That means if it is a low angle, that means less resolution. Resolution is not too much. You cannot see it as a separate image. So this is the case of the picture A. In the case of picture B, you can see the cone is much more wider. So here the angle is 7 degree and the numerical aperture is 0.12. That means low resolution. അതായത് numerical aperture കൂടുന്നതനുസരിച്ചിട്ട് resolution കൂടും. If the numerical aperture is greater, that means better resolution. So in the picture 2, the angle is mu, or the alpha is 20 degree and the numerical aperture is 0.34. And the third picture, a little more wider cone here, so the angle is 60 degree and the numerical aperture is 0.87. So if you consider these three pictures, A, B and C, which one has a greater resolution? The C has the greater resolution. Why? Because the sin alpha is greater, or the angle of aperture is greater here. So thus the greater numerical aperture, so the greater resolution. And if the cone light has a very wide angle, in the picture C, this picture, very wide angle and spread out rapidly after passing through the specimen, closely packed objects appear widely separated and thus resolved. Now the angle of light that can enter the lens depends on the refractive index of the medium as well as upon the object itself. Two factors. So one is the object placed here and the second is the medium, which is the air here. So if the air is the medium here, its refractive index is 1 and the maximum numerical aperture you can get is 1. It cannot be more than 1. So if you അപ്പോൾ ന്യൂമറിക്കൽ അപ്പർച്ചർ എത്രമാത്രം കൂടുന്നു അത്രയും എൻ്റെ റെസൊല്യൂഷൻ കൂടും. ഇഫ് ഗ്രേറ്റർ ദ ന്യൂമറിക്കൽ അപ്പർച്ചർ the greater the resolution. But if the air is the medium, the maximum numerical aperture you get is 1. So beyond you can't increase the numerical aperture. So therefore only the practical way to increase the numerical aperture is above 1 is to increase the refractive index by using an oil. You change the medium. If the air is changed, if you add here is the specimen and this is the objective lens, and between you add. So the bottom surface of the lens should touch the oil. There should not be an air between the specimen and the lens. So that if the medium is completely surrounded by the oil, then the refractive index of the oil is greater. This is all. The refractive index of the oil is 1.515. So we can get a wider angle here, and means at a better resolution. So in conclusion, the better resolution can be obtained by LM can be increased by taking into consideration two factors. One is called you decreases the wavelength, and also you increases the refractive index and the angle of aperture. That means the sin alpha. If you increases, so these two factors helps to have a better resolution.